In this video, I'm going to show you how to use the program for multiple curve plots. I'll come down here and click the button for it. When I do, a set of instructions appears in the description box, and then we're going to be inputting information into the input values box over here. Now the program plots multiple curves on the same plot, often to illustrate the moderating effect of a variable on the relationship between two continuous variables. Suppose I find the effect of consumer attitudes towards a product on consumer repeat purchasing behavior of that product over time varies as a function of ethnicity, that is, for Asians, blacks, and whites. Specifically, suppose I observe the following regression lines. I can see there's an interaction effect that's operating here, that the effect of the attitude on behavior is stronger for Asian than it is for blacks than it is for whites. So these are the equations that I want to plot in this program. The program can plot up to 5 different curves or 5 functions, and I'm going to put the 3 functions here under curve 1, curve 2, and curve 3. And you only enter the right-hand side of the equation, and you always refer to the independent variable as capital X. That's very important, otherwise you'll get an error in the program. So for Asians, the intercept was 4.0, and the slope was 0.50 times X. It's very important I put in the multiplication sign there because the program is literally going to take the equation in this box and apply it as it's written. For curve 2, or for blacks, their intercept was 3 and the slope was 0.30 times X. And to show a little shortcut, I'll just highlight that and copy it and then paste it here, and then make the edits where their intercept was 2 and the slope was 0.2. I leave these functions blank because I'm not using them. It's very important that you use the functions consecutively, that I don't have spaces between them like I do a curve 5, a curve 2, and a curve 1, leaving curve 3 and 4 blank. That will create a programming error. The low and high values of X that I'm going to use are 0 to 10, so I enter the low and the high with a comma in between. The label for the X-axis is attitude, and the label for the Y-axis is behavior. Now this can present the regression lines either using different colors for the 3 groups or different dashes, and a 1 means to use color and a 2 means to use dash. That's described in the description box, but if I want a little reminder, I can hit the toggle switch here, and that'll give me the key. And in this first case, I'm going to use color. Okay, I'm going to hit register input to create the syntax. I'll copy that to the clipboard. I open up R. Here I'm going to hit Control V to paste the syntax, and as it is pasted, it'll execute. And over here is the plot. Here's the legend down here, and then there are the 3 regression lines. Now if I don't like the way some things appear on here, I can always copy and paste this into a graphics editor and edit things accordingly. For example, I might right-click on this and copy it as a bitmap file. Windows has a graphic program called Paint, and I can open up that. I'll hit Control V to paste it, and there's the plot there. I can zoom in on it a little bit, make it a little more accessible. And let's suppose I don't like the position of the legend down here, so I can select that, and then I can drag it and put it anywhere I want to. I might put it up here at the top, or I can put it over on this side or whatever. And let's suppose I want to use labels of Asian, black, and white instead of the equations themselves. Then what I could do is I could select these and hit delete to erase them. Then I go up here and I create a text box. type in the word, I'll take off the bold. I'll type in the word Asian. And then I create a second text box with the word black. And a third text box with the word white. I then select this box. I select this and put it there next to Asian. I select black and put that there. And then I select white. And I put that there. And then let me go to view and zoom out a little bit. And I can select the entire plot. And then I go to home and hit copy. And then I can paste that into PowerPoint or into a Word document and resize it within there. So let me close this out. And let me close this. And come back up to the input box. Now you can also use the program to explore nonlinear functions. And let me give you an example of that. I'm going to clear out the entries of the box. Now suppose I have people read material to increase their knowledge about a new product, such as a vaccine. I measure their knowledge on a knowledge test that ranges from 0 to 100, with higher scores indicating more knowledge. The knowledge they gain will decay over time due to forgetting. Suppose I measure their knowledge at different points in time to see how much the average level of knowledge changes with time. I measure knowledge for some people right after they've been exposed to the material. Others I wait 1 month to assess their knowledge. Others 2 months, others 3 months, and so on, say through 8 months post-exposure. I do not use a repeated measure design because if I keep administering the same knowledge test to people, that in and of itself can influence their performance on later knowledge tests. Now, I do not necessarily expect the decay in knowledge to be linear. A widely studied function of forgetting is based on the work of Ebbinghaus, and it's represented by this equation here. That knowledge is a negative exponential function of how many months, of the number of months since exposure, where exp stands for the exponent of the month divided by a constant b, and then we have a constant a over here. Now these constants a and b are much like intercepts and slopes in linear regression. Here's the linear regression here. If I thought the decay was a linear function of time. And this constant is the intercept, and this constant is the slope, and we estimate those. Now I want to get a sense of the curve that this equation implies, and I can use the multiple curve program to do that. Now before doing so, let me mention one property of this equation that's important to keep in mind. It turns out that any number raised to the power 0 is equal to 1. So if the number of months since exposure is 0, then the exponent of 0 will equal 1. And that will give us a times 1, which is a. So a is simply the average score on the knowledge test immediately after message exposure. It's all downhill from there in terms of decay. But keep in mind that this parameter here, a, reflects the average initial knowledge score of people. Okay, so let's go back to the program. And I want to see what are the implications of that b parameter. So I'm going to create different curves where I vary the b parameter in that equation. I'll use as the initial knowledge score right after message exposure a value of 60 out of 100. So I'm going to have 60 times the exponent of minus x, that's months, divided by b. But in this case, I have to define b, and I'm going to set it in this curve to be equal to 3. Then I'm going to take this same function and I'm going to put it in curves 2, 3, and 4. But now I'm going to set b to 2 here. Here I'm going to set it to 1. And here I'm going to set it to 0.5. So I can see what are the implications of changing that parameter on the forgetting curves. The values are going to range from 0 to 8. So I enter those values comma delimited. The low score is 0 and the high score is 8. Those represent the months. The label for the x-axis I'll put as time, and the label for the y-axis I'll put as knowledge. And then I can either use color or dash. I'll use color in this case. And then the equation box I just leave blank. I hit register input to generate the syntax. I come down to the syntax and hit copy to clipboard. I start R. I hit Control V to paste it. And over here are the plots with the different curves. This line is when b is equal to 3. Here it's equal to 2. Here it's equal to 1. And here it's equal to 0.5. And you can see what the effect of b is doing is that larger values slow down the rate of decay. So here's the curve when b is equal to 3. But when b is down here at 0.5, you can see there's very fast decay. And then it levels off. This is not quite as fast, and then it levels off, and so on. I can fit this equation to data using the nonlinear regression program on the web page, and it'll actually, based on the data, estimate the value that A and B should have in best accounting for data. So this program can also be used to explore nonlinear relationships as well as to show interaction effects. Okay, that's it. Thanks.